These videos are offered on a pay-what-you-like basis. You can pay for the use of the videos at my website. There is a link to my website in the info box. The address is www.freelance-teacher.com/videos.htm, or you can just use the link in the info box. By the way, I also offer tutoring via Skype, and you can find more information about that Skype tutoring service at my website. Thanks. We're going to start with the Baeyer-Villiger reaction. The key reagents here, of course, we're starting with an aldehyde or a ketone. That's the kinds of compounds we're looking at now, aldehydes and ketones. But the other key reagent is a reagent that looks like this. Now, this is a type of reagent we talked about briefly last term. I don't know if you guys remember what would be a good name for this type of functional group.
No, I'm just kidding. It's either an ester or...
Let's go over that. Now, we briefly saw last term that this is the formula for carboxylic acids. We didn't talk about it much. That's going to be very important in this week, carboxylic acid. This is a carboxylic acid. But this is not a carboxylic acid because it has two oxygens bound to each other. We briefly last term talked about situations where we have two oxygens bound to each other. Do you guys remember what we call it when we have two oxygens that are bound to each other? Those would be, in general, peroxides. When we have two oxygens bound to each other. Remember, per means a lot or above. Well, peroxide is when you've got a lot of oxygens, two oxygens bound to each other. This is a type of peroxide, but to be more specific, we would call it a per-acid because it's a variant of a carboxylic acid, but it's got this peroxide group, so it's called a per-acid. I guess the full name would be peroxycarboxylic acid, peroxycarboxylic acid, but for short, we can just call it a per-acid. This is the general formula for a per-acid then, when we have the two oxygens bound to each other. It's an extension of a carboxylic acid. Another way this could be written is like this. So we'd have to be able to recognize this way of writing the per-acid as well. This again indicates two oxygens that are bound to each other. And we could condense it even more like this. And again, we have to recognize that this means a per-acid, and we need to use outside knowledge to recognize that one of these oxygens is a carbonyl oxygen and the other two would look like this. So all of these would be good ways to write per-acids. We have to be able to recognize all of those. Clearly then this is a per-acid. This would be per-acetic acid. I think last time we talked about what does acet mean?
Two carbon.
Yeah, except for acetone, acet means two carbons. So this is acetic acid. This is per-acetic acid because it's a per-acid with two carbons. All right. The per-acid that we talked about most last term was, I think, MCPBA. We talked about that when we were dealing with alkenes. We won't go through the whole name here, but this stands for per and this stands for acid. So this is a variant of a per-acid. We won't go through the whole structure right now. What did we learn to do with per-acids last term? We learned that we could make alkenes into epoxides using per-acids. We're using this as basically like an oxidizing agent. So, and that might still be a useful reaction this term. So last term we saw that an alkene plus a per-acid gave us an epoxide, or what we called an oxycyclopropane. Alkene plus a per-acid gives us a epoxide, also called an oxycyclopropane. That was the reaction we saw last term. Well, that's what per-acids do to alkenes. Now we have to learn what do per-acids do to aldehydes and ketones. And they actually do something similar to what they would do with an alkene. This is the basic reaction we learned last term for what a per-acid does to a alkene. It basically inserts an oxygen between these two carbons. It breaks one of the carbon-carbon bonds and inserts an oxygen between them. That's why we could think of it as an oxidizing agent, making new bonds to oxygen. Well, in this case, we're again going to insert an oxygen. The per acid is going to insert an oxygen between two carbons in the aldehyde or ketone, and it looks like this. It inserts an oxygen between the carbonyl carbon and the alpha carbon. That's the Baeyer-Villiger reaction. This is the Baeyer-Villiger reaction, and just like a per acid inserts an oxygen between two carbons in an alkene, here it's going to insert an oxygen between two carbons in the aldehyde or the ketone. Which two carbons? The carbonyl carbon and the alpha carbon. Remember, we saw this is not the alpha carbon, this is the carbonyl carbon, this is the alpha carbon over here. So I showed this working on a ketone, but it would work on an aldehyde as well. Now, your instructor may expect you to know the mechanism for this, but it's in the textbook and it's in the second language books. That's not the best use of our time right now. In most cases, you're not going to draw the mechanism. In most cases, it's very much simpler just to draw the product. So we'll just go over how to draw the product.
We do need to know it, but yeah, we can go over that in a second.
Okay, so here is our. So we've simply shown how we would insert the oxygen here. Right, well, we can do a couple. Let's see. Does that make any sense so far? Yeah. Okay. So. You said you were assigned some problems on that?
Yeah.
So.
48, 49, 47. So 48, 49, 47 are all blue. And where's G?
Wait, you said the mechanism for this is in the second language book?
Yeah, and it should also be in the textbook. Or is it actually?
It's not really.
Yeah, you're right. It is in the
They just
second
have
language
one
book.
part.
They no, it is in the textbook.
It is?
Yeah.
Page 769?
You have a different edition than me, but yeah.
Oh, yes, it is.
Right.
Okay.
So let's see the problems you were assigned were.
And then it's also these two. Those gave.
Those are not, are those Baeyer-Villiger reactions? I don't really recognize those as
They
Baeyer-Villiger.
gave oxinoic. I guess that we can ask that besides that.
Okay, so let's start with this. Let's just draw the product from this reaction. It should only take us a second. Let's just make sure we have the basic idea. And we can draw the product here.
Doesn't matter if it has the VF.
What question is this?
This is just a simple made-up example to make sure we have a basic idea.
Does the F matter in this?
Turns out that it doesn't really matter exactly what per acid you use. I'm just trying to show the range of per acids that you could use. This is one of the per acids that was used in the book. But no, as long as it's a per acid, we should get the same reaction. Now remember that this is going to insert an oxygen between two carbons. Which two carbons did we say it's going to insert the oxygen
But there was
between?
no two carbons over there.
No two, I don't...
It just added an oxygen and another carbon at the end of that.
Yeah.
Oh, in this case, did it? Well, let's go back. I don't think
Oh,
that's.
no, it didn't. There's a carbon at the carbonyl and a carbon over there, and now there's an oxygen.
I see what
Okay.
you're doing.
Let's try to articulate which two carbons are we going to insert the oxygen between? What would be the names?
Alpha
Yeah,
and carbonyl carbon.
that's right. Well, that's what we did here. We took this alpha carbon, and now the alpha carbon has moved out over here. Maybe it would help to put in some numbers. 1, 2, and 3. In this picture, the number 2 and the number 3 are no longer connected to each other. The number 3 used to be the alpha carbon, but now there's this oxygen in between it and the number 2,
Does the
the
matter
carbon.
which one it chooses to be which alpha?
Now, in some cases it would. In this case it doesn't because these are symmetrical to each other. So let's start by getting the basic idea down, but then we can come back to your question, which is a good one, which is often tested. What happens when it's not symmetrical? Let's get the basic idea first.